concentrated ore to the reducible metal form. This was just nothing but the removal of the gangue from that ore. First, what we need is we need to convert the concentrated ore into a reducible form, which can be easily reduced to the pure metal. For example, we might have concentrated it, but still it will be in sulphide, carbonate or hydrated form, which must be converted into its oxide. For that purpose, we are having a conversion to metal oxides. We are having calcination process and roasting process. It's the next stage. First stage is concentration of the ore. Next stage is conversion into its oxides. First, calcination. Calcination means heating in the absence of air or lack of oxygen, the decomposition of the ore to oxide or volatile water is lost in that case, like ferric hydrated, it converted into ferric oxide. Next is zinc carbonate, decomposes to zinc oxide. Calcium carbonate gives us calcium oxide and magnesium oxide. Roasting. Roasting is nothing but heating the ore in the regular supply of air at a temperature below its melting point. Like we heat the ore in this ample supply of air. Zinc, lead and copper, which are important ore, exist as sulphide. Remember, zinc, lead and copper exist as sulphide ore. And like zinc sulphide goes to zinc oxide, lead sulphide goes to lead oxide, copper sulphide goes to cupric oxide. We heat this copper sulphide ore, what will we get? Copper oxide, which is the reducible form. If the ore contains iron, it is mixed with silica too. Why? Because silica will make slag, silicate slag with iron that can be removed. Purification of metal oxides to metal. That requires supply of electrons, because metal oxides are in a cationic form or their oxidized form. For their reduction to a pure metal requires electrons from reducing agent. That's one option. Or we have to supply electrons externally in electrochemical cell. These are the two possibilities of the reduction of oxides into metal. Thermodynamically, reduction of metal oxides should follow. Gibbs free energy should be negative for it, for the reaction to be spontaneous. Only then reaction can proceed from forward direction from oxide to pure metal. If delta S is positive for this such reaction, on increasing the temperature T part, Ts value will increase, it will be negative, and increases, then delta G will become negative. So with increase in temperature, there is a greater chance for the reaction to be spontaneous, or oxide will convert it into its metal. For any particular reduction of metal oxide, for which delta H is positive, means change in enthalpy will be positive, reaction will not be feasible. So for such reactions, if delta H is positive, for me to make it spontaneous, it must be compensated by T delta S, change in entropy and temperature. That's what the reaction is. Energy changes will become feasible only at high temperatures, as change in entropy and at high temperatures will compensate for this positive delta H, and reaction will become spontaneous at delta G is negative here. Ellingham diagram helps to explain the oxidation of certain metals and non-metals. Using that, we can really find which element can be suitable for a reducing agent to reduce other elements, oxide. This is called the Ellingham diagram. From left to right, metal shows delta G is equal to negative. So, for reverse of reaction, it will be delta G will be positive. These are the oxidation diagrams, Ellingham diagram, and we see delta G is negative here. So reverse of it will be positive. From delta H, values for any chemical reaction remains nearly constant, even on varying temperatures, where delta S changes with change in phase. So in chemical oxidation reactions, above diagram is mainly temperature dependent. We have to understand that in these diagrams, temperature is a main factor for reducing any particular element of interest using other element as a reducing agent. Let's take an example of zinc oxide. This is a zinc oxide diagram, and zinc is having a delta G negative, it's reducing, it's here. Delta G is negative actually. This is the oxidation diagram. CO. This is simultaneous. You see at this point, around 800 degrees Celsius, coke getting into carbon monoxide. Somewhere here at 673 Kelvin. In the presence of carbon, zinc got reduced. Why? Because the reverse of zinc oxide is reduction here. It means it will be positive at this temperature. It must be compensated by other element like here zinc, carbon, which getting oxidized into carbon monoxide. So it's like coupling reaction in which this carbon got coupled with zinc oxide. It has got oxidized itself, but this is spontaneous, and zinc oxide to zinc is non-spontaneous, and the energy supplied by the oxidation of carbon is used to reduce zinc oxide to zinc. That is what Ellingham diagram says. Similarly, reduction of iron oxide, hot air is blown from bottom of the furnace and coke is burned to give 2200 Kelvin temperature in the lower portion of this furnace. We feed ore, limestone and coke in that from the top. Gases escape from it. Hot air is fed from the bottom. As a coke burns, it heats up the upper portions. And ultimately what happens? CO is formed. That heat moves to the upper part of the furnace. When the temperature is lower, iron oxide comes there, got reduced. We're getting a molten iron and pig iron. Which are collected. What are the properties of molten and cast iron and pig iron? Pig iron contains large quantities of carbon and having many impurities, so its strength-wise is weak. Cast iron is different from the pig iron. It is having a lower carbon content and made by melting the pig iron with scrap iron. It having a low carbon 3% and very hard. That's why many tools are made from the cast iron.